Hi, everyone. Thanks for watching this talk. My name is Rafaela Gsponer, and I'm a PhD student at the University of Portsmouth. Thanks to the organizer, I today have the opportunity to talk to you about my most recent project, which is early dark energy in the light of logically structured data. And maybe let me just start by telling you why we think investigating extensions to lambda CDM as early dark energy is very interesting at this specific moment in time. One of the most pressuring questions in cosmology at the moment is the Hubble tension, where the Hubble tension refers to the discrepancy of measuring a value for the expansion rate of the universe in either a direct way, as it's done by shoes and leading to a high value of H0, versus an indirect way, as it's done with Planck measuring it from the CMB, which leads to a low value of H0. So if we think about how could we actually address this tension, we need to think about what kind of cosmological assumptions go into inferring H0 from the CMB. So that's why let us just start with a short recap of how we actually infer the expansion rate today from the cosmic microwave background. Planck, measuring the temperature fluctuation of the CMB, gives us a very precise measurement on the spacing of these peaks in the temperature fluctuation. And this spacing can directly be translated into a constraint on the angular scale theta s at lost scattering. So we have a sub-percentage level on this angular scale, but this angular scale actually is a result of a ratio of two other quantities. One would be the sound horizon, and the other one would be the angular diameter distance to the surface of lost scattering. And although this ratio needs to be fixed, this kind of tells us how we can think about modifying models in order to address the Hubble tension. One way would be to change the sound horizon, which we normally talk about as early time modification, versus the other one would be thinking about how we infer the angular diameter distance, which corresponds to late time modification. And if we just look at the CMB, actually in both categories, we find solutions to the Hubble tension. It comes though when we then actually compare it with other data sets, as we've seen here on the right, especially with baryonic acoustic oscillation, where it gets really hard when it comes to modifying and bringing all these different data sets into agreement. Because we can think about the Hubble tension not just as a tension in H0, but also as a tension in the sound horizon, or in this specific plot as a tension in the drag horizon. So in order to bring Planck, this tiny gray contour in this plot, into agreement with not just BAO, but also distance ladder, we actually not just need a higher Hubble value, but also simultaneously a lower value of the sound horizon. And this is kind of like giving us an idea how we can actually modify lambda CDM. Because the BAO, they track the expansion history very well, so late time modification suddenly become very, very hard. While early time modification are actually able to simultaneously achieve a higher H0 value while decreasing the sound horizon at the same time. One model that actually acts in this early time modification way and leads to a decreased sound horizon is the model of early dark energy. In the model of early dark energy, we consider an extra scalar field. This very light scalar field is initially frozen, acting like dark energy, before it overcomes the Hubble friction and starts rolling down a potential hill, injecting energy into the overall energy budget of the universe. One thing that needs to be guaranteed in this model is that this degree of freedom decays fast enough to not make any impact on the late time physics. Because although we want to change early time, we are very happy with the expansion history and how things evolve at late time. So we don't want to play around with this. So if we think about early dark energy in a phenomenological way, we normally describe this model with 3 additional parameters on top of lambda CDM. One would be how much early dark energy do we have? How much overall energy is injected into the budget of the universe? This is normally defined by if we want to resolve the tension purely by early dark energy. In this case, this value needs to be around 10%. Another thing is about like how fast do we need to have this exascalar degree of freedom to decay, which can be tracked by the equation of state. And last but not least, when is this early dark energy actually becoming important? This is kind of defined that we want it to have an effect on the sound horizon. So if it acts too early, the effect is minor, while if it acts after recombination, there will be no effect. So we also needing to act in a specific redshift range. So now we can go and take this theory model and actually compare it to data and see what the data is telling us. This has been done with Planck. So getting constraints from the cosmic microwave background on early dark energy. And it was great. We found that the temperature fluctuations of like the fitting to the temperature fluctuation of the CMB is achieved by early dark energy as well as by lambda CDM, while simultaneously, as we wanted, H not pushing into a regime where it actually overlaps with the constraints of the distance ladder. So overall, we were happy, right? But obviously, this was not the end of the tale. Otherwise, we would not be here. Because people then started comparing large-scale structure to early dark energy and getting constraints from early dark energy. And this is the point where early dark energy then starts to face problems. Because in order to keep this great fit to the CMB, other cosmological parameters change in the model of early dark energy. One that I especially want to mention, or two that I especially want to mention, is NS and AS. So the overall amplitude of the power spectrum, which then actually worsens another tension which is present in cosmology at the moment, the so-called SA tension, describing the discrepancy of measuring the clustering in our universe when we measure it from the CMB versus when we measure it from recleansing data. And as you can see in this contour plot, we see the green contours coming from Planck already pushing slightly to more clustering than what we observe with recleansing. If we now look at this with early dark energy is kind of like pushing into this direction even more, favoring even higher clustering. So when we look at early dark energy and large-scale structure data, suddenly the questions arise. Are we just like tension trading? Or can we solve the H0 tension, but are we just like facing and making the sigma A tension worse? That's why the overall goal of this project now would be to use a full shape analysis of eBOSS and eBOSS data to put constraints on early dark energy and kind of conclude, or at least hint, if early dark energy is still a valid model to describe the Hubble tension if we combine it with large-scale structure data or not. Why we want to do a full shape analysis versus the more standard compression analysis is that, as you can see from the plot of Colin Hill et al. In 2020, that we can tell the difference in the power spectrum of the early dark energy versus lambda CDM, especially when we go to very small or to very large scales. The very large scales are not accessible to us. So what we would like to do is we would like to use the full shape analysis to fit the overall power spectrum, accessing the getting access to these smaller scales where we actually can tell the difference between early dark energy and lambda CDM. A reason why we want to use eBOSS data and why we hope eBOSS data will be able to put tighter constraints on this is that you can see again from the plot that when we go up higher in redshift, this difference gets bigger and bigger. With eBOSS, we are covering a redshift range from 0.7 up to 1.5. So we really hope that with like including these data sets, we can put tighter constraints on early dark energy. Let me just tell you how this full shape analysis is done in a nutshell. So as I said, with the full shape analysis, we would like to fit the overall power spectrum. We have theoretical prediction for the linear power spectrum, but when we then go and want to push into these nonlinear scales or mildly nonlinear scales, things become harder. The thing is, if we want to do perturbation theory, the quantity that we want to do perturbation theory in is not fulfilling one of the most important conditions to do perturbation theory, because the overdensity field of dark matter actually not remains small when we go to smaller scales. So what we actually do is we're handling this with an effective field theory approach called effective field theory of large-scale structure, where we kind of look at the K range where we know that our theory is valid, and where we can address this by modeling the dark matter field as an imperfect fluid. So we have the linear terms, but then we can also go to the next leading order, having integrals, like giving us an average weight contribution from all the other scales on one specific scale. These integrals would go up to infinity. As I said, we can't go up to infinity because the theory breaks down. But what we can do, we can kind of split the integral into two parts. One where we actually, in the theory, know how to solve the integrals, and a high-end UV tail, where we actually not being able to analytically solve the integrals, but we can find a parametric form for these integrals. As you can see in this section UV, we then kind of fit this UV tail by including counter terms, which we need to fit to the data in order to find the value of these counter terms. And like this, we kind of get a complete theory in the K range that we look at. Overall, we don't observe the direct dark matter field. We are looking at bias traces. So we are including stochastic counter terms and a nonlinear bias scheme to then model our bias traces. If we then look at the overall setup of our analysis, we can get the linear power spectrum from an Einstein-Boltzmann solver code like class EDE, which has this extra scalar degree of freedom integrated. And using this effective field theory approach, we can push this linear power spectrum into mildly nonlinear scales. Using an MCMC sample like MontyPython, we are then actually able to compare our theoretical prediction with the actual data, getting posterior distributions on cosmological parameters, but also on our early dark energy parameters. As you can see here on the right, I produced a synthetic data vector which looks like eBOSS data, but artificially has 12% early dark energy in it. And as you can see, the pipeline is able to recover this 12% in early dark energy while also recovering the truth values of all the other cosmological parameters. So before moving on to actual data constraint runs, we now spend a lot of time investigating one big challenge that the EFT of large-scale structure actually has to face. The EFT of LSS has 7 nuisance parameters. So we talked about these counter terms, the galaxy bias, and the stochastic parameters. And it was shown in the literature that depending on the prior choices that you put onto these nuisance parameters, you actually see shifts in your posteriors. Here on the right, I show ECMOX for LRGs, where I'm setting a Gaussian prior. And as you can see, we are not able to perfectly recover the truth, although within 1 sigma, we are within the truth for omega matter and sigma 8. Why are we choosing the Gaussian prior here is from a theoretical argument saying that these counter terms need to remain small, otherwise the theory itself breaks down. And what we mean with small in this context would be that these counter terms should be of order 1. Now, I just want to highlight that we especially see a shift in sigma 8, which can become very important when we then do our early dark energy analysis. Because as I mentioned before, early dark energy itself shifts sigma 8 to higher values. So for us and for the early dark energy analysis, it's very important to understand if and when we see a shift in sigma 8, is this due to a detection of early dark energy and like forced by the early dark energy parameters, or is this something that actually just depends on the prior choices on these nuisance parameters? So we spend a lot of time on this. In the end, we decided to not just use a Gaussian prior and do the more like standard analysis with a Gaussian prior, but also include a Jeffreys prior analysis into the final EDE constraints. Why we are replacing the Gaussian priors on these nuisance parameters with a Jeffreys prior is because the Jeffreys prior, as defined here, where F is the Fisher matrix, is actually able to at least partially mitigate these projection effects that we see. So you can see it on the right, the contours, orange to blue, shift back to the truth. And this is exactly what we want for our early dark energy analysis. And with this, I conclude. So the current state of this project is actually that we did these pipeline testing, and we did spend a lot of time thinking about the right prior choice for these early dark energy. The data runs are running at the moment, so maybe at the moment where we have the parallel session, I can tell you more about the actual results. But for now, I just want to mention again that early dark energy is still one of the most promising solutions to the H0 tension. And it will be really like coming down to if early dark energy is able to fit large scale structure or not. Thank you very much.